Hey, it's me, Destin. Welcome back to Smarter Every Day. This is the first video in a series of videos on going back to the moon. The fun thing is, I have no idea what these videos are going to entail because the opportunities have not presented themselves yet. But I do know this. I know NASA, with the Artemis program, they have set their sights on the moon, and I'm all about it. So if you're a contractor, a program manager, if you're NASA, and you have things you want to talk about landing on the moon, I'm your guy. Just give me a call. We'll do a video about it here on Smarter Every Day. So that being said, let's think about this. I want to talk about the specific technical issues that have to be overcome in order for this to happen safely. So number one, if you think about a lander descending to the surface of another celestial body, you basically have to solve the equation of velocity equals 0 when you touch the surface of the moon or whatever, right? So that's been done before, right? When the Apollo astronauts descended to the surface of the moon, they actually piloted the craft all the way down, and they made sure their velocity equals to 0 right at the moment that they touched down on the surface.
Contact light.
So how did they do that? It seems like a simple question, but it's very, very complicated. The reason this is so complicated is here on Earth, we are being pulled down towards the Earth at 9.8 meters per second square, 1 g, right? Well, on the moon, it's 1/6 g, 1.625 meters per second square. So think about that. If you have a spacecraft and you have a rocket on it, it's going to behave differently on the moon than it does here on Earth. So how do you practice landing on the moon when you're on Earth? Many scientists and engineers among us right now, they have the knowledge of how we went to the moon. But what we need to reclaim is the understanding of why we made the decisions we made along the way. And that is a task well suited for the scientific historians among us. Let's start this whole series with one of the most authoritative sources on the history of the lunar lander program that I can imagine. It was a lecture given in 2007 in front of the Society of Experimental Test Pilots by none other than Neil Armstrong. Let's go get smarter every day.
In January of 1962, FRC proposed a free flight lunar landing simulator program consisting of 3 parts: a preliminary study, a research test vehicle, and an Apollo flight simulator. The research test vehicle would be small, relatively inexpensive, and independent of the actual Apollo configuration. It was intended to investigate the inherent problems of lunar descents from altitudes of up to 2,000 feet and have the capacity to vary control characteristics, cockpit configuration, displays, and landing gear geometry, and so on.
Neil goes on to explain that in the 60s they were thinking about the problem of descending to the surface like hovering a helicopter, so that's where they started. The problem with a helicopter, though, is it changes the way you move laterally. Let me explain. If you think about a helicopter, it has to offset its own weight, right? So if you've got the weight here, then you have lift that's pulling it up at a certain amount to offset that, right? If you decide to translate forward, meaning you want to tilt the helicopter forward and you want to move in that direction, you still have a vertical component of lift that's going to offset that weight, but you also have this horizontal component that will let you accelerate forward. Now that makes sense on Earth, but the problem is if you're in a spacecraft and your spacecraft has 1/6 the weight of a helicopter, even if they're the same mass, you have to go with me here. Think about it. If you have a very small thrust required to lift that thing, if you tilt it over and try to translate in the same acceleration moving forward, it's not going to work because as you tilt that thing forward, the horizontal component of your acceleration is far lower because you're not thrusting as much. So in order to get the same acceleration in the horizontal direction, you would have to tilt the spacecraft over much farther than you would a helicopter. This is the problem they had to figure out how to solve.
They considered a helicopter and a lunar vehicle of the same mass. Over Earth in the helicopter, and if there were no drag, the horizontal component of acceleration would be approximately proportional to the tilt angle of the rotor. Over the moon, where there is definitely no drag, and weight is only 1/6 of Earth, the same amount of acceleration requires nearly 6 times the tilt angle.
Another problem they had with helicopters is the way you had to do the test. For example, if you're just hovering above the ground and you're descending in a straight line, that's a very difficult thing when you're close to the ground because you're inside what's called dead man's curve. Basically, in a helicopter, you want to have enough altitude or velocity to be able to auto-rotate to the ground if you lose power. I made another Smarter Everyday video about that if you want to check it out. But long story short, helicopters could be dangerous for this specific test application. After the helicopter thing, they tried an experimental aircraft I didn't even know existed in the 50s and 60s.
The X-14 might be a useful simulator, some thought, although it could not duplicate the effects of reduced gravity.
Yes, what you're looking at is a vertical takeoff and landing airplane in the 1960s.
Its reaction control system was quite variable and could replicate a wide variety of control characteristics that were directly applicable to lunar flight. Some lunar final approach simulations were performed in early 1964, but without the lunar gravity characteristics, they were of limited usefulness.
I didn't even know the X-14 was a thing. That's incredible. Anyway, it didn't work. Neither did the helicopter. And the whole reason is this 1/6 G thing. So what do? If every vehicle you put a pilot in is 5/6 too heavy, you have to take away 5/6 of the weight. And if you think about the perfect physics way to do it, you'd have like an infinite string going straight to the sky that would pull 5/6 of the weight up. But that's like a very difficult engineering problem. Think about it. If the pilot was over like commanding things, as the pilot moved, that string would have to remain directly overhead, because if it didn't, you would start a pendulum oscillation. That's like an impossible thing to build, except NASA built it.
Independently, at NASA's Langley Research Center, an alternate approach to lunar simulation was initiated. The Lunar Landing Research Facility, LLRF, looked like a dirigible hangar after a tornado. Again, the idea was to duplicate the lunar gravity and control characteristics. The method was to lower the vehicle apparent weight to its lunar equivalent by lifting upward with a vertical cable attached to a traveling bridge crane. A complex electro-hydraulic system kept the crane platform directly over the machine and the cables vertical with an upward force equal to 5/6 of the vehicle weight. It had a wonderful assortment of structural and cable stretch and pendulous frequencies requiring innovative compensation networks. It was indeed an engineer's delight. After the kinks were worked out, it worked reasonably well. The flying volume, 180 feet high, 360 feet long, and 42 feet wide, was limiting, but it was adequate to give pilots a substantive introduction to the lunar flight characteristics.
So the LLRF was awesome. It gave pilots like a first order approximation of how to fly this thing, but any pilot will tell you that's still not flying. Like when you're in the seat and you have total control of the aircraft, there's something different that happens in your head. Like for example, at the LLRF, if something didn't work, you could just hit the emergency stop button and you would just swing, right? Like everything would lock up, it's not a big deal. However, free flight was preferred, and they still didn't know how to simulate this until an apparent answer came out of NASA's Flight Research Center out at Edwards Air Force Base. Interestingly, the FRC, as it was known, is now renamed the Armstrong Flight Research Center.
The proposed technique for simulating the lunar gravity was simple in principle. Reduce the apparent weight of the craft to its value while flying over the moon. The proposed method: install a jet engine underneath or within the machine on gimbals, so the thrust was always vertically upward. The engine thrust would then be adjusted so that the craft's net weight, that is its gross weight minus the engine thrust, would equal its lunar equivalent. The force required to lift the net weight would be provided by throttleable rockets. And so the Lunar Landing Training Vehicle, or LLTV, was born. It featured a partially enclosed cockpit with a LEM-like visibility, a 3-axis control-mounted side stick, a lift rocket throttle replacing the collective LEM displays, a rate command attitude hold system that closely approximated the expected lunar module performance. The LLTV proved to be an excellent simulator and was highly regarded by the Apollo lunar module crews as necessary to lunar landing preparation. But it was unforgiving. 3 of the vehicles were lost. NASA management was forever worried about the reliability and safety of these machines and continually wanted to shut them down. But the pilots insisted they were vital to lunar landing preparation, and they prevailed.
So this is Ben Feist. Ben has an amazing website that he created called Apollo in Real Time. And Ben, how long did it take you to make Apollo in Real Time?
Apollo in Real Time took a very long time. The Apollo 11 version took 2 years of work by a whole team of volunteers.
2 years. And basically you took every piece of footage across the whole mission and you synced it together so I can go in and listen to a specific person on console. Was that the idea?
That's the idea. Anything that's in the historical record should be there, timed to the moment that it occurred.
I know, because I've seen this and I've talked to you a little bit, I know that you have the entire mission memorized. Is that fair to say?
No, that's not fair to say.
It's pretty dang close.
I'll go with it.
It's pretty close, dude. You pretty much have it memorized. So here's my question. So basically they slow down and come out of orbit and they start descending. And once they do that, are they pitching more over in the lunar lander than they would have in the LLTV? Or do you think the LLTV was a good simulator for what they were doing?
The LLTV was an excellent simulator for that exact problem on the moon, in that you're tilting much more than you do when you're hovering on Earth. And the simulation, the other simulations that they trained for, like looking out the window and seeing the lunar surface and using the flight computer, weren't all pulled together until they were actually in lunar orbit and doing it in real life.
When you watch the Apollo 11 descent, does it feel like they've been there before? Like, do you feel like they were adequately trained?
They were very adequately trained, and Neil Armstrong was a test pilot who actually helped to develop the training protocols for how that worked. So him being the first one to do that was perfect in that he was good at academically assembling different training protocols, and the astronauts were adamant that they should be allowed to fly the LLTV so they could get that experience before they were actually at the moon.
Even though there was danger?
A lot of danger, and actually the danger was a big component also of why the LLTV was important, is that it put their hides on the line, as they would say, and gave them that aspect of maybe your heart pumps a little harder than it would normally when you're flying something like that gives you the simulation of the kind of danger that they were in when they were landing on the moon.
I actually have some footage here of Neil Armstrong talking about the LLTV after a flight, and he's very clinical in how he speaks about it.
What was your actual time up there, Mr. Armstrong?
Gosh, I don't know. I suspect it was around 5 or 6 minutes.
5:59.
5:59, they say. The question was, how does the machine fly? And the answer is that we're very pleased with the way it flies. It's a significant improvement over the LLRV, which we were flying here a year ago. And I think it does an excellent job of actually capturing the handling characteristics of the lunar module in a landing maneuver. It's really a great deal different than any other kind of aircraft that I've ever flown. It's the simulation of lunar gravity has some aspects that make this type of flight sufficiently different from anything else we've ever done to make this vehicle very worthwhile. And I'm very pleased that I've had the opportunity to get some flights in it here just before the Apollo 11 flight.
Quite a bit of noise, I gather, up there.
Well, it sounds a lot noisier outside the vehicle than it does sitting on the inside. The noise radiates out in all directions, and since I have this helmet on that has a good bit of soundproofing in, why it really isn't too loud, although communication is a problem for us. We have the radios picked up pretty well now, and I could maintain communications with the crew here. That's a very important part of this operation. Since it's a training vehicle, we use telemetry, and the people on the...
That interview that you just watched took place exactly 1 month prior to launch of Apollo 11, which means even though NASA management thought that flying the LLTV was dangerous, they viewed it as an overall risk reduction technique for the mission in general. They thought refreshing the algorithms in Neil's brain was a smart thing to do just prior to launch, and it worked. Here's the thing though, we are actually going back to the moon. So that being said, we know how to build an LLTV. But what we don't know is why they built certain things the way they did, like the decisions that were made. Basically, knowledge of how to do it is not understanding. I wanted to speak to someone who actually does have the understanding of why all these things took place. So I did a little bit of digging and actually found one of the engineers that was over the LLTV program. So I'm so excited to share this with you. Let's go speak to the man who literally wrote the book on the LLTV, Mr. Wayne Ottinger.
Hello?
Hey, is this Mr. Ottinger?
Yep.
Here we go. I just sent you the invite.
Okay, I'll get up and get to the computer.
We're going to talk to the man, like the guy who designed the LLTV. You talk about excited.
Can you hear me?
Yes, sir, I sure can. So can I ask you a couple of questions about the LLTV?
Yeah.
So if I understand correctly, you guys were offsetting the LLTV's weight by 5/6 with the jet engine, correct?
Yeah, we had a real challenge because we were thrust limited on the available jet engine. It was a 4,200 pound fan jet that had just been commercialized. It was a J85 core, but it had an aft fan on it.
I could talk to you for hours. I really could. So here's a question. So when the turbine was spinning up, or when the jet was spinning up, did you have issues with gyroscopic precession?
Yeah, we did. We percepted our yaw rockets were firing, consuming rocket fuel to counteract the gyroscopic force. And so what we did was to put a small port on the bleed air of the compressor and piped a little 12-pound thrust out of the bleed air to counteract the gyroscope. That was a common design for all of our LLRD. And
you bled off a little bit of it and shot it to the side so you could counteract the spin.
Right.
So let me ask you this. If the LLTV had the jet engine going up through it like that, then you had a certain attitude that you could roll to before you would
plus or minus 40 degrees in pitch and roll.
40, so that you would gimbal lock, so to speak, after that.
Yeah, we have pitch and roll gimbals.
I've watched the video of Neil Armstrong punching out of the LLTV so many times, but I have no idea why he did it, and I can't find a satisfactory answer online. Not only was Wayne there that day, he has intimate knowledge about what happened, and he even spoke to Neil Armstrong immediately after.
That was a human error on the accident because the ground controller was too timid to tell him to. I had an engineer behind him telling him to knock off the lift rocket. He was running out of fuel. Guy which I didn't train very well. I take some responsibility for it because I didn't guess that he would be so dumb. But he let Neil run out of fuel, and he let him run. I had designed the tank so you could never lose. You could always have 20 pounds of peroxide to feed your attitude rocket system and never let the lift system run out your attitude control. But what he did was, without paying attention to the radio, he just let Neil leave the lift stick up and blow all the helium overboard, so he had no pressure to push out the reserve attitude fuel. So he had to eject.
I was going to ask you that. When I look at the ejection of Neil, I thought it was a PIO, a pilot-induced oscillation. But you're saying he was out of pressurant on his peroxide.
He lost total control of the attitude because that's why he pitched up and then punched out. And then that afternoon, when we picked up the wreckage with the crane, the snake rolled out from underneath the fire. And it was half burned. I always wanted to make a cartoon about it. What the hell was that?
This is from the snake's perspective?
Yeah, I wanted to make a cartoon. Never did do it.
Mr. Ottinger, I know that I need to let you go, but I would like to ask you two more questions, and these are big picture questions. Thank you for how generous you've been with your time. But first big picture question is, so back in the day, the engineers and scientists on this program did amazing things with limited
analog electronics.
Right. So do you think that engineers in the 50s and 60s were better than engineers today?
No. No, I think we all had our unique place in history, and they'll continue to be new challenges met, and there'll be innovation that continues. And part of it's because they can build on our shoulders. They can learn from what we did and then adapt to the new technology and so forth.
Do you think something like the LLTV needs to happen to train astronauts to go back to the moon?
They aren't going to go if they don't get a free flight trainer, I can tell you that.
Really?
Yeah, they won't go without it. They know the value. They're smart enough to know.
Now the United States is planning to return to the moon. And when that craft is on final approach to that flat-tip ridge near Shackleton Crater, I hope that the person at the controls has a simulation experience that is at least as good as the LLTV provided the Apollo crews a half-century later. Thank you.
I hope you enjoyed this episode of Smarter Every Day. Maybe we'll get to look at more landers in the future. I don't know. We'll see how that works out. But I want to say thanks to the sponsor of this episode, which is Audible. Now, I'm going to do something a little bit different this time. Usually I tell you a book that I've read before, but this is the rare time where I'm going to tell you a book that I downloaded today that I'm about to start reading myself. It's called Carrying the Fire by Michael Collins. When Neil Armstrong and Buzz Aldrin touched down on the moon, it was Michael Collins who was orbiting the moon, waiting to pick them up. Michael Collins, if you know anything about him, is known for his humility, his poise, and his wisdom. So I am looking forward to this because a ton of people have told me to listen to it. I downloaded it today. I'm not hesitating to tell you about it because I'm looking forward to it. So please consider getting that by going to audible.com/smarter or texting the word smarter to 500 and a little link will just pop up on your phone. Click that and then you can just go get Carrying the Fire by Michael Collins. There's an incredible selection of audiobooks to choose from. You can also go to the Audible Plus catalog. If you're an Audible member, you get a credit every month for any book you want. However, you can get as many books as you want from the Audible Plus catalog. So you can have thousands of included titles at your fingertips. It has changed my life. I am devouring audiobooks at an incredible pace. I downloaded 2 today. I'm going to listen to those over the next week, but you really need to be listening to audiobooks. It makes you smarter and helps you reclaim your time. Audible.com/smarter or text the word smarter to 500. Thank you very much for supporting the sponsor. When you do that, that supports Smarter Every Day, and I am grateful. I'm grateful for you. Thank you for watching Smarter Every Day. Please consider subscribing if you feel like this video has earned your subscription, because I know that is a precious thing you don't just give away. But if you'd like to, there's a button somewhere and you can click a bell or whatever. If not, no big deal. Anyway, I'm Destin. You're getting smarter every day. Have a good one. Bye.